And welcome back everyone for this second part, for this Eve uh, courses, discovery, panel, and so on. In this next session, we are going to speak about how we can use Eve at a slightly higher level using algorithms first. And then we are going to try to see how we can use Eve in non-trivial settings, like um, dealing with non-trivial types like structured data, and how to write codes that we like stencils and things like this. Okay, and so we are going to see how we can go up to having archetypal Grace code implementation using Eve. So we saw just before that we have a lot of functions. We can use them with different options. We can use them on different types. We can handle different size of register and whatnot. So the question is now is what if I want to express more complex situation? And the classical way of doing this in C++, in modern C++, is to use algorithms. Standard algorithms, range algorithm, and so on. So Eve provides a selection of SCMD, aware, let's say, call it this way, STD-like algorithms. Okay, that will be able to handle for you all the complex tasks of running the loop, ending alignment, handling the tail at the end of the loop, and provide way to tune the algorithm depending on the architectures with respect to, for example, the way you want to unroll the loops, or even if you want to unroll the loops, how you can manage the problem of performances with AVX512 cores and so on and so forth. And we have a slight, a lightweight data structure to handle with that. So we are going to see a bunch of those, a bunch of algorithms, a bunch of views, and we are going to speak about structure of array and how we are in Eve very committed to this model of programming. But before going into the deep end of that, just try to see why we want to do this. Because, I mean, probably I can take any standard algorithm, that lay around, and just either let the autovectorizer do its jobs, because it's there for that. Or maybe I can use, std parent sec or something like that to force my compiler to generate unsequenced and so forth vectorized algorithms. And so probably whatever we do there is useless, okay, right? Yeah, except not. Let's have a look at a very simple algorithm, which is findIf, okay? So in this benchmark, we try to find a zero in an array of 100 bytes, okay? So the size is very small because we want to be sure that we are not affected by L2 cache miss and whatnot. It's in bytes, so we can see the impact of the actual size over the basic benchmarks. So basically, the blue line is ST-defined, and ST-defined takes sometimes about 240 something for char, down to 80 something microseconds for 32-bit integer. And we see that the bigger, the object we are looking for is, the faster we go because we consume more bytes per cycles, okay? And what happens is that if you run Eve algo findIf, okay, that will vectorize, okay, findIf, okay, a different way to do that. Well, we don't care because we are always consuming 128 bits, what's inside, okay? So we have this very flat, just below 10 microseconds of runtime, whatever the type is, which is on AVX2 a speed up of about 23 or something for chars and around 6 or 7 for integers, which is quite good. But okay, that's fine. But if you look, and that's what we are going to see as an example, if you look at other, let's say, easier algorithm, like transform, reduce, and stuff like that. Maybe, maybe we are not going to be that good. And indeed, we are going to see that depending on what happens in our loop, our best shot will be to be as fast as the autovectorizer or slightly faster. And on the other end of the spectrum, maybe there is, like algorithms that make no sense vectorizing or for which there is no way to get proper, performances. Oh, I know which one. Remove if, okay? STD remove if. You pass it a data set, you pass it a predicate, and you remove the value from the data set if it validates the predicate. And what you get at the end is a compressed data set where every surviving values are close together, there is no holes, and you return the end of the now compressed data set. So there is no memory allocation and so forth, but we have something that we don't know each iteration how many value we are going to keep. So definitely this is not something we can vectorize. Well, turns out, we can actually. I won't go into the details, but let's just say that there is a way on almost every architecture to do this compression quite fast with different mechanisms. So sometimes it's an intrinsic, sometimes it's a trick using shuffles, okay? But we can do that actually. And we have a very nice benchmark there. I like this very much. The time there is drawn upon the percentage of value that is equal to the value we want to remove. And we have these scalar bumps around 50% because what happens? Well, at 0% stuff to remove, you never do the if. You always take the if the correct way, so you always predicted your branching correctly, and so you go fast. And as soon as you go up to 50%, your branch mix prediction increases, so your speed decreases. And as you go down the other way around, you start predicting that you need to take the other branch of the loop, of the if, up to 100%, where basically you are fast also. So it depends on branching. But turns out we have a way to branch in SIMD mode. Okay, we have a function called if-else that is vectorizing if-else. Okay, and we don't care about the branching because there is no branch. Okay, it's all conditional execution of the code. And so we have this very flat at the bottom speeds. And so this is about 1,000 microseconds compared to 25,000 microseconds. So again, a speed up of about 24, which is good on this machine. So we have this very large setup of algorithm. I wish I could show you the documentation. It's currently a bit sparse due to some doxygen errors we are trying to find out. But we have a bunch of them. Let's see if we can actually just have a quick look. Let's go there. Okay, and just so you can see the how to say that, the scope of what we have. Where are you? Are you there? Yes. So we have a bunch of them. We have predicates, we have copy, if equal, fill, find, for different versions of for each, inclusive scan, iota, keep if, which is basically remove if the other way around, computing of min and max, mismatch, none, and so on and so forth, and reduce, and a bunch of others, transform reduce also, which is very interesting. So we have a large selection of algorithms, and we also have a large less large, but large anyway, selection of view like zip, reverse, map, convert, and so on that lets you look at your data set in a way that is actually more complicated than that. So we can do that. So let's have a look at how it can actually work on an actual use case. Let's say we have that. Okay, we have this process scalar function. It does some computation. Okay. And what you want to do is you want to use if to vectorize it. So we are going to transform input into out, okay? And we call this lambda. Okay, so I'm trying to go very slow because the process is very complex. You can do this, and you do that. And what you want to do is call if algo there. We actually have two transform in place and transform to, because there is a slight optimization we can do there, and we are done. So let the thing compile, and it should be practically done. So this is where I should have put a small, elevator music in the background, but here we are. And as I said, there is no surprise. We have a speed up of basically nothing, because I hope every compiler is able to optimize that and auto-vectorize it. Okay, and so if we have a look at what the auto-vectorizer does, it does something. He even knows that he can use that. That's cool. What do we do? Oh, and then he does the tail. What do we do? Well, we do some stuff at the beginning. We are going to speak about that later. And then we have 1, 2, 3, 4. We have unrolling by a factor of 4, okay, which is basically there. And if we look, we mul sub add div. Oh, turns out we don't use FMA. Okay, but that's something we can easily fix. We are going to see that. And the actual interesting thing, this is actually, where is it? Yeah, this is actually the compact loop. Okay, this is what is going on in the innermost loop. And so the question is, what do we add before? Because if you look around, I know it's a bit complicated, but if you look around, there is no mul SS. There is no scalar computation. We are going to go back on that a bit later. So, or maybe I should unroll a bit less, because if I look at the regular cases, the auto-vectorizer didn't vectorize. So we can actually, because if algorithm, like if function are actually callables, we can put some options there. And so we are going to use the unroll function, the option, to say, okay, what about I don't unroll? Can do that. And yeah, we are going to compile for a bit. So a bit more elevator music at this place. So Pierre, if you are in the back, probably we should hire some kind of, orchestra for next year doing this. Okay, we are slightly better. So apparently not vectorizing helps. And as we see, the auto-vectorizer know about FMA, and apparently we don't. So let's teach that. So what are we doing there? We are going to do E times E plus 1. So this is a multiply add in the correct order. So let's just call multiply add. Multiply add between this and 1. Let's see if it goes faster. This is another issue, but let's see if we go slightly faster. We are already 10%. Oh, that's worse actually. But we were actually 10% faster like a few seconds ago, so it's not that bad. Let's see if FMA actually helps. The game is how much things should I write to get close to whatever the auto-vectorizer was doing. So it's slightly worse now. Okay, fine. Probably because we need to complete the thing. So this is multiply sub. Okay, and so we have the whole, we have the whole family, like multiply add, multiply sub, add, multiply, sub, multiply, negate of multiply add, and whatnot. There is like 6 or 7 of them. So we are at what? 5%. So we are back to where we were. Okay. Let's see if I force a recompilation. So another great thing you can do, yeah, it's not that good, okay. Another great thing you can do using Eve is that you can use evalgo to get some free time, when you want to do something else while we compile. You know what, let's see what we can do there. What kind of other option do I have in my algorithms? Where are you? Okay, let's dive into this. So we have a bunch of options. So we saw nothing there because it needs to be like very bigger than that. So we have the unroll things, okay. We can force the cardinal of whatever we want to compute. You can force the type in which we want to compute. That's another thing. And I'm trying to find out. So no unrolling is basically this. Yeah, no aligning. Because if we go back there, okay, and we have a look at the small thing there, we saw that we do a move, we move unaligned. Okay, we load unaligned data because the auto-vectorizer doesn't want to care about whatever this thing is. What we do is that we try to care about loading stuff aligned as much as possible. And so we have some prologue up to the point we know we can actually have a full-blown, where are you? A full-blown, alignment, loading, and storing, and whatnot. But this adds a bunch more computation. It's not a line anyway, so maybe we can just tell the algorithm that we don't really care about all these aligning things. So we can probably say just don't align, just don't force the alignment of your data set. Okay, so let's see if it's better. Okay. So one thing we try to do, as you see, is to isolate the fact that you want to write the actual math there in a way which is orthogonal to actually writing, the definition and whatnot. So we are basically at the same thing now, which probably means that we generate probably the same code now. Okay, what is that? Okay, so this is the main loop. Okay, now we load unalign, and then we have this. We try to finish what we started. Okay, in these cases. Okay, and because we don't enroll, but we don't know how many things we have, and so we have then the end of the tape. Okay, so we are basically at the same speed now, so which is exactly what I expected to get. So we saw that we get a small amount of changes, but this 10% is actually not meaningful. We are basically going at the same speed. So let's do the devil's advocate. So all of that for nothing. That's very cool. Thank you for playing. Okay. Obvious, but it was obvious we are going to go there. Now let's see what happens if we do a bit more complex operation. Let's just be mean and say we need to compute this. And then we can say, oh yeah, I know how to do that. I can just call have x there and see what's going on. So most of our complex function, complicated function, I need to be careful with the things I said, is like exponential, logarithm, trigonometry. They all are based on some different kind of polynomials or sub-series approximation, okay, depending on what we do. Sometimes with a reduction of the input, so we can compute stuff faster and then reconstruct the whole value. So it's usually better than whatever the poor autovectorizer is going to do. So if we do x now, we have a bit more computation going on, and we saw that we start having a speed up of about almost 5.8, which is almost 6. We are dealing with AVX2 register of float, so we should have a speed up of 8. So 6 over 8 is what? 72%, something like that. Okay, we could actually compute that in the display, maybe. Let's do that. Let's compute the efficiency of these things so we can get that, because I will spend my whole hour trying to guess how much is that much percent. Okay, so efficiency. So this divided by what? Why the float size, probably. So we have something which is actually architecture agnostic. Okay, and this is percent because it's efficiency. Yeah, so let's do that. So okay, so if we go with more complex function, obviously we start having a bit more interesting speeds and so on. Yes, so did I forget to multiply by 100? I did forget to multiply by 100, whatever. So we can do that. Okay, that's the way to do this. But exp is a complicated function. You've got a bunch of corner cases, and the Eve exp, like a lot of basic math function in Eve, it tries to do its best. Okay, right? And as we saw, we have way to make it faster. Okay, we have different levels. We have the raw level. We have the fast level that can ditch precision or whatnot to get better speed. So let's see what happens if I try to do that the stupidest way possible. So if you want to play at home, try to think how you can actually compute the exponent of something, okay, without doing some Taylor expansion or whatnot, or using a proper Remez expansion of these algorithms. So we got like 13 speed up. We got twice faster, so we just blew up the thing. We blew up the speed up because we go faster because of SIMD, and we go faster because we have a funky algorithm. The funky algorithm is based on the EEE 754 representation of a floating point. So there is a funny way to compute this by forcing the exponent into the exponent bits. Okay, so it involves bitcast and whatnot. It's a funny algorithm to write. So let's see what happens if I don't know, if I remove that, if I remove those options and I go back to this very simple function call. So we were at times 13, which is not bad. It's basically times 10 and some bonus, so it's one order of magnitude. And again, okay, we don't do any OpenMP, we don't do any MPI, we are not on the GPU, we got a 10x from our own CPU. That's exactly what we want, right? It's slightly better for some reason. Oh yeah, X is probably big enough, so we have more opportunities of, you know, interlacing things during the enroll. Okay, fine. So we can do that. Okay, and again, the cool thing is that the math is there. Okay, we can decide to do this. Let's see what GCC does. So let's say 14. Okay, 13.8. That's a good score. Let's see if GCC is better or worse. Maybe GCC know how to vectorize X. Maybe not. We don't know. That's a surprise. Yeah, well, spoiler, it does not. Okay, and so we are slightly lower with GCC, but it's probably just the variation of the whatever. But the question I have actually is maybe GCC is a bit smarter, and does it know about the FMA there? That's the question. Sometimes compiler sees that you have an FMA and it generates an FMA for you. Sometimes it does not. We strongly advise to, if you really want to get the bonus point from FMA, to call it explicitly. Okay. We could also play around with the data size and whatnot. Yeah, so do we have a FMA now in our vectorized code? Where are you? That's a lot of people going there. Okay. Am I inside already or not? I was. Okay, no. Process English. Yeah, I was not. So what happens? Do we get the... Oh, we get the free FMA actually. So GCC sees that sees the FMA, generates an FMA and whatnot, and here it goes. Okay. Let's see. Yeah, in some other places it does not, but yeah, it does the thing. Okay. So depending on the compiler, sometimes you don't need to have to put it, but it's clearer. So if you put it whenever we want. So let's go back to Clang. Clang was slightly better actually. We could play with lesser extension or bigger one if you want, but we are going to be around those time 14 something, which is not that bad. Okay, yeah. But then again, and I think I heard the question or the remarks last week when I was scouting the Discord channel. It's all fine and dandy, but what if I want to do something a bit more complicated than that? Because I'm all for processing floating points and double and whatnot, or integer in a single vector, or a span, or whatever. Turns out sometimes I need to have, I don't know, like a 3D position, or I have to have a pixel with tricolor as unsigned char, or whatnot. Okay. Stuff like this, actual data structures. What do we do with that? Well, yeah, we need to work around that. Okay. So this is something we need to have a look at. Where am I? Okay. So let's see how it works by trying to do something very simple. What about I want to work with, let's say, STD complex? Very simple stuff. I need to have a complex number, okay? I want to, I don't know, like compute its norm using iPod or whatnot. Okay. So we can actually do that. Okay. Let's. I'm going to spoil that for a while, and we are going to see how it works. So this benchmark is a bit more complicated. I put some optimization barrier so we can have an actual benchmark run that works. Okay, so you have that in your example file. It's not very important. It's probably something you already spoke about and whatnot. So what do I want to do? Well, I have a vector of complex float coming in, and I want the vector of its magnitude. Okay, so I'm going to do what everybody should do, computing the iPod between the real and the IMAG part of the complex number. It gives us some codes, okay? And actually, if we go down there, let's see what process scalar looks like without doing anything. Yep, whenever. So iPod is basically the square root of r squared plus I squared, but with proper precision and handling and whatnot. So you don't end up with none or nth as soon as your complex numbers are very close to 0 or I or stuff like that. So whenever you want. So what does process scalar does? Yeah, it completely drops the balls because it's just called iPod. So now that's the place where you should remember about fast math. This is probably because iPod touch the global error code whenever you do something stupid with your value, so it has to do this. So normally we should win a lot. But the question is, how can we do the same thing? Okay. Well, let's start with something simple. I know how to write SIMD code using Eve using regular types. So I can actually write this. I'm going to take a function with two vectors as an input, so real and IMAG part. So we manually somehow force the code to be into some kind of, structure of array, separated mode. Okay. And so, a bit like we would have done that using STD algorithm in Vue, we can zip the two vectors. Okay, so now this element is actually some kind of a tuple that contains, as we saw there, every time both a part from the real and part from IMAG, and then we call iPod. Simple enough. Yeah, but what if I want to have something that actually behaves like a complex? So turns out that Eve wide is compatible with types that follow the tuple protocol. So tuples, okay, or tuple-like object, stuff like pairs, okay, and whatever struct for which you manually implemented the tuple protocol, which is having a get function, having a tuple size, a tuple element, and whatnot, which is the basic way we have since C++17 to make our data structure able to be used that way, by the way. Turns out, inside Eve, we use another library of mine, which is called Kumi, which is a small a large reimplementation of tuple and tuple algorithms that happens to be out of the block compatible with Eve. That's a good idea we had. So let's start simple by saying that a complex is basically a tuple of two floats. Could have been a pair or whatever. Okay. We are going to see what happens if you try to use STD complex by itself. Okay. So it's a pair of floats. So now what I can have is I can actually have not a vector of complexity, but this thing, a SOA vector of complexity. If SOA vector is a container that behaves just like vector, except it only accepts types which are actually compatible with the tuple protocol, and it will automatically behave like vector, but store everything in an automatic SOA manner. So we have a SOA vector of complex, and basically we get whatever the complex is there, and we can pass it to iPod. A lot of if functions have these properties, that is that if you have a regular element-wise operation like add, mul, iPod, square root, and well, square root is not very useful, but stuff like this, power, that takes multiple parameters. You can also pass a tuple of set parameters directly. So if you want to multiply 5 elements, you can pass 5 parameters to mul, or you can pass a tuple of 5 values. It's a sort of compile time broadcast, if I can say that, or compaction, depending on the way you saw it. So we have a tuple-like object there, so we can pass it directly to iPod, which is very similar to what we, it's actually better than what we did there, because we don't even have to unpack it. We could, but we don't even have to do it. And iPod is a very complex function again, and so we can actually ask for a faster iPod. What's the difference? This is doing a lot of precision handling, okay? This is basically square root of the square, the sum of the square of the parts of the tuple. So this is very, very, very raw. So if you have stupid values, you get stupid results. But it goes faster. Okay. And again, we can wrap that into transform 2 using either something that is already a SOA container, or we can build your own using zip. Oh, and by the way, because I saw people probably in the back trying to raise a question, yes, you can zip whatever type you want. I could have made a tuple of 2 floats and a char and whatnot. And we know how to compute the best number of lengths for this composite type. And you don't have to do anything. Okay. So in this case, yeah, we got float because it's complex of float, but we could have more complex system like this. Okay, and then we bench. So what kind of result do we have? Well, not that bad actually. So the Scala version takes about 1.40 something, 46 something milliseconds. When we zip it using the regular iPod, we go basically almost 8 times faster, 7.2. That's, oh, come on, I should have put the thing back. I forgot about the efficiency, which is the only interesting metric there. Let's have a look. How much is that? 7.28 over 8? Yeah, it's like 91% efficiency. That's good. Yeah, that's good. Zip and SOA basically do the same thing, because internally it's the same thing. Okay, add some details, but I mean that's as the third decimals. And when we say that we don't care about the precision, because most of the time when you want to go fast, you don't care about precision that much, we can go actually 20 times faster. So if you have very well behaved complex values, very close to magnitude of 1 or something like that, you can actually raw iPod them and you can get like 20 times faster. Okay, but we spoke about it. What if I sabotage myself by putting a fastmat there? Normally, the autovectorizer should do better. That's what we think. But does it? Okay. And are we able to have some leverage against a code compiled with fastmat? Eve is actually able to detect fastmat itself. And so whenever you compile with fastmat, we say, okay, you compile with fastmat, you know what? Maybe what we are going to do is to use the row or the fast lane directly because you just gave us the permission to do so. So we also know how to interact with those compilation options. So what does process scalar does? Yeah, it doesn't do anything. Okay, so Clang doesn't know how to vectorize iPod even using fastmat. I'm kinda sad about that. And we get basically the same results anyway. So it's not a case where we can win much there. Okay. So we can do this, but I mean, maybe complex is already compliant with the, the tuple protocol. Let's have a look. Let's try to do this. If it is, I should be able to do that. RI about SED complex 4.5 and 6.60 point whatever, we don't care. I said we don't care, but a bit more than that. So does it actually compile even? That's a question. And apparently nope. Oh, the solution guide. Oh, come on. Come on. Okay, one more deception. Yeah, I mean, binds one element, which is very strange because it should be, right? So complex doesn't look like it does. Let's start to see if we go further in time. because I remember having a discussion about that recently. So let's see. Yeah, SLA complex is not compliant with the tuple protocol, so we are a bit screwed. Yeah, he's not very happy about that. Yeah, I mean, we break a lot of things. Let's see if GCC has a bit more leverage on that. There is a paper about the fact that complex should be a tuple, but I don't know where it ends up. The answer is nope. Okay. So whatever. So too bad for us. We can even do that, so we can do this. That's a bit of a pity. But you know what? That's not that big of a deal. So as we said, we can do that. Okay, that's a complex number stuff. So the variant we have. As I said, in this place I unzip. I just destructor to pass it, but as we saw, we can actually just pass it directly. And for those of you that are very sad that STD complex, sorry for the strong word, is basically a pile of manure. Okay, we have Eve adjacent library called Kyozu, which implements some kind of Cayley-Dixon algebra for computing over complex quaternion, octonion, and whatever is beyond octonion if you really want to. Yeah, it's basically complex, but with a decent, thing. So you can find it on GitHub if you want. It's still not. It doesn't have a release yet because we are still working on the documentation. But let's, if we look at the example, that's exactly not where I wanted to go. Just so you can have a look at that. Okay, not there either. Doc. Yeah, we have a bunch of whatever, including those big functions, stuff that makes sense when you know what it is. Let's have a look at, I don't know, what X. Yeah, we can get that. Yeah, and so we have the complex quaternion cases, and we can mix match wide, scalar wide, and whatnot, different kind of concepts, and we can just use them directly as a type inside wide, and we have a SOA implementation of those types. So if you want to have a look at that, you can up there and see if you like the things. Yeah, so we ended up having to do that because SCD complex was a mess. It doesn't have like half the function we need. The reason why we have that, so you can see the bigger picture, is that we are also working on a library called Fluxion, which is not out here, which is basically using Kyozu and its complex and quaternion numbers to implement some kind of forward scheme for automatic differentiation, whatever, and all vectorized. So we have this kind of expansion that goes over there. So if you want to dig these complex things, you can have a look at that. But let's do something else. What happens if I have a more complex data structure? Like let's do some high school physics. We all, know and love our good old Newtonian physics. Okay, I should make an example with relativistic physics at some point. But basically, what I want to do is that I have a ball. My ball have different properties. I know where it is on the z-axis. It's a position. I know what its speed is along this axis. It has some elasticity coefficient because it will bounce back. And I'm going to count how many bounces I'm making. Okay. And so what you can do is you can use Eve through his Eve struct support struct to do a bunch of curiously recursive template patterns there to say that your ball is actually that. Okay, 3 floats and an integer. And this gives you everything. It gives you the data set inside, which is a tuple of all of that, and it puts all the required types and overloads so that it's tuple compliant and it's Eve compliant. All those functions are basically just helpers. You don't even need them because you can std get directly on it. But it's better to have them because we get a bunch more, semantic. We have this concept like T that basically says that you can pass whatever there as long as it's either a ball or a wide of ball. Okay, that's the way we can consume both scalar and SIMD type of this. So this is an actual SIMD-enabled data structure. So now we can do some simulation. So I have a ball coming in. And I'm going to do some very bad physics there. I should be using some actual integrator, but I have only so much time. So I'm updating my position by taking my delta time and multiplying by the speed. I put the gravity back on the speed, and then I check if I bounced. Okay, if I bounce, I'm going to switch my speed sign and multiply by some coefficient. And I count on the fact that I bounce. So if you look, I update the falling ball and I compute the new bounce ball cases. And then I need to know what happened after my update step. And what we say that if the position of the falling ball is very close to 0, we are going to snap on some grid, and we say that we are going to bounce. So we use the bounce value now. Either we are going to use the falling balls. And we have this if-else coming up. Okay, they say, okay, if this is true, I'm returning this or I'm returning that. Okay. And so we have this simulation step. Now what can we do? We can have an object of update. Say, okay, I have that dt, my gravity is whatever, I have some maximum amount of bouncing. What do? Well, I'm taking my SOA vector of balls, I unroll a bunch, and I transform it in place using the behavior object. So for every ball into the balls vector, we are going to vectorize this operation of simulation and update it. And after some amount of bouncing, we consider that we don't care about some of those balls, and we remove if. That gives us the end of the memory space where the correct data are set, and we do an erase from there to the end to remove them physically. That's the classical erase remove idiom, okay? That still work on our SOA vector of whatever. And what happens if we have a look at the function itself? Well, a bunch of things happen, but at some point I have, where is it? Some sort of very dense loop. Okay, that's the main loop. I need to unzoom a slightly tiny bit. Yeah, so we go from there to there. And we have the mud, al, sub, zor, mul. This is some computation of comparison, and then we update. So this is basically what happened there. So this is AVX2. Let's put some FMA inside. Do we get the FMA? I don't think we have FMA. We don't have FMA, so it's probably useless. Oh, I know what we are going to do. Yeah. So let's see what happens if we go like Sapphire Rapids or whatever. Some big ass, AVX512 architectures with a proper number of P. That's probably that. So I don't touch the math. I don't touch anything there. I'm just changing the compilation option, and I get a new compilation with different subset of intrinsics. I'm not going to make it run because it's a bit long and it's not very funny if we don't have any kind of display. But you have it in the Eve examples in the GitHub, and so there is some actual bouncing display. But what happens? I ask for AVX512 and I end up with AVX2, which is okay, but that's not what I ask. Yeah, because AVX512 causes CPU to slow down when you start processing AVX512 intrinsics. This is the AVX512 speed penalty. That is something that is, alas, well known. But turns out we know about it, and we have different way to get around that. Okay. What's the name? Oh, frequency scaling. Okay, here it is. So we have yes, we have this option. Okay, where are you? Is it you? Nope. Is it you? Nope. So that's you? Yes. So I can ask transform in place to be called with what we call the frequency scaling option. That say basically I don't care about whatever, AVX512 is doing. Okay, I just want to go faster. and I want to have LXI12 things going on. Okay, and now, do we have some ZMM going on? Do we? So we have Y there. Oh, did we fail again? Oh, we failed again. Ah, come on. Oh, yeah, because I'm stupid. Okay. I'm not at the correct places. Arch equal. So if we don't use LXI12, obviously we don't use Sapphire Rapids. Sorry about that. Oh, probably duplicated the window. So if we allow for frequency scaling, that's basically only have any meanings on x86, but here they are. We should have some ZMM going on. Okay. And do we? Yeah. Now we are running LX512. Is it better? Is it not better? We have to test that, but we know how to generate it also, and we got whatever we need to get there, including where are you? Where it is? Yeah, including some conditional move and whatnot. Okay, so we can go that far in terms of data structure handling. Okay, so we do data structure. We do where are you? Oh, I lost my slides. Do I? Did I? Oh, I did. Oh, because I probably do this. Yeah, I did. We do that. Now, what happens if I want to do something other? Let's talk about stencils, because we know we are going to do stencils at some point. So this is another filter. This is the bilateral filter. It's a funny one-dimensional stencil operation that you can use in image processing. It's basically some kind of smoother filter, but that doesn't generate sharp edges whenever you have a big difference of intensity, by using some exponential computation. Okay. So we saw that it's a stencil because we have this I plus j thing. So we have some kind of neighborhood there, and we do this exponential compute a weight. We do some weighted sum, and we finally end up, doing this. So it's a 1D filter like that. So how do we handle stencil using Eve? Currently, we don't have any stencil-enabled algorithm because I will be very frank with you, it's very complicated. You can emulate them using zip, but you don't get good performance out of that at some point anyway. So what do we do? Well, for every point of the stencil, we are going to load a different wide, and then we are going to replicate this exact computation, inside a wide. So we load some data from the image. We do the same computation, loading with the same differential position, and we do the same computation, and we do the x and whatnot, and we do that. And as we do it by hand, we need to handle the tail ourselves. Spoiler, if you have to do that, look that my scalar version takes a span and not a vector, because I can then reuse it as a tail handling by computing some subspan from my original span of data. That's a cool trick because you don't have to duplicate the code about that. So let's have a look at how it looks when we try to run it. Okay, so this is not that. This is not that. Nope. Yes. So that's the bilateral filter benchmark. Okay. So again, that's the one you have in the Docker. You can play with it, play with the radius and whatnot. This is a very big radius, by the way. Okay. And yeah. We have exactly what we saw. We have two variants from Eve, the regular one that has the regular x and the one with the raw x, obviously. And we see that we got some decent speed up there using what? AVX2 and FMA. Okay. Speed up of 4.3 something because x is costly, and if we go the raw x, we go better. And in this case, using a bad precision x is okay because we are generating pixels in the end. So your eyes is not going to see any difference anyway. So we can do this. We can do stencils. But in 1D it's easy because we can do one stencil per whatever, okay? let's do something while I'm speaking. Okay, what if I have a very small radius now? When you have a 2D stencils, like we have in the Grayscott operation, you see that you have to have, if you have a 3x3 stencil, you are going to need to load explicitly 9 wide. And if you have two things like the, exactly like the Grayscott, the U and the V, is it done? Oh yeah, it's done. So it's basically the same thing. You are going to need a way to manipulate this large amount of whites. That's why we want to have something that is actually common. Workable as, yeah, we don't care about that. Where are you? Oh yeah, I know why it's not there, because I need to run it on my actual machine. Let's just have 1 sec. So let's see the code on my actual machine, because it's not going to fit into the thing. So again, you have that into the Docker, so you can play with it around. So we have some, preset like the size, the value of the coefficient, and whatnot. Pierre, I hope they are the correct one. If not, I will look stupid, but whatever. Somewhere else, we're going to have our stencil, which is basically over there. So we have those points, okay. We got some utilitar values. We don't really care about that. And so we have this 2D 3x3 stencil going on, where we read into U and Y, we do the computation, we do the update of the output, we update the border and whatnot. Full-blown things. Then we can do the same thing with Eve, and we decide to do a bunch of unrolling and a bunch of FMAs and whatnot. That's the core kernel. We load U and V, we do some computation, and then we load every other parts, depending on where we are in the U and the V, and so we get multiplied by the stencil. We do some more FMAs, and so on and so forth. We could actually probably be able to factorize all of that, and then we do the computation, and we store at the end. We have another one where we put FMA and FNMS everywhere, okay. And then we have the bench things, okay. And so the question is, how much do we get? So let's see, have it compile, okay. Oh yeah, that's probably a good idea to add some kind of, include pass. I forgot about that. And by the way, so we are a C++20 library. I didn't speak about it. If you forget about that, you will get an error message that say you should enable C++20. So okay, so how big are we? Let's see. So scalar, some FMA, some enrolling, some more, and so on and so forth. Let's see what's going on. So we have two levels of unrolling, different way of handling FMAs and whatnot. If you remember last week, you should see that it may depend. And so the scalar is actually auto-vectorized. So we have to be very careful with the number we have there. This thing is auto-vectorized. Yet, when we use some mix of stuff, we can get to 1.6 times faster than the auto-vectorized version. Okay, fine. Let's go over our LX512 machine, where normally I should already have, I already compiled some of those. Let's see if it's the same version. Yeah, that's the same version. Oh, we don't have the mixed one there, because we know what we should be doing. Or I can actually take that and recompile it completely. Okay, let's see what happens when we unroll or don't unroll, and see how far we can go there. Okay. Okay, $10. It's not the correct version. Yeah, no, that's not. It's not working. Okay, let's do that. Probably not the correct version. Not a big deal. Let's do this exact same version. Okay, and yeah, let's go up there. Oh yeah, yeah, I know why it's not good. Okay. At some point, I tried to get something like with different level of things, but it's not what I want to do. So what am I? I am a rocket lake. This one is a rocket lake. So let's do that. And we should have something comparable. If I'm not mistaken. Yes, that seems better. Okay, let's go. Yeah, and we go twice as fast as the auto-vectorized version with the biggest things of 800 and almost 10 megacells per second of update. So even in the face of a complex how to say that, complex operation with slides, with stances and whatnot, where the auto-vectorizer is able to do great things, we are able to get some decent extra performance. You can play around with it, play with the size, play with your architectures. Let's see how it behaves. Okay, it's an interesting thing. So it's probably time to conclude now. What did we saw? So we have this library called Eve. It provides us a path to explicitly vectorize code by also providing some guarantees about the performances. If you write regular code with regular operation in a way that makes sense in terms of CD, we got you and you got some decent performance. We have extra API for algorithms, for data structures that we keep improving, okay? And so we can actually play around with that. We have tag release. We are closing up to getting an actual version 1, probably this summer, now that we know how to compile on Visual Studio and fix a bunch of API issues. Okay, so I encourage you to test it in your own project if you're interested with that. If you have bugs, just report them. We try to solve them as fast as we can. You want some function, you want some architectures. We are all open to add things if you want. If you have strange hardware and you want to support it, if we can have access to it, we can probably make a port, and so on and so forth. The workflow we recommend is trying to find the places where, after, for example, a benchmark or a profiling, you see that you are lacking vectorization while you should have it. Okay, so a big shout out to the people from Macau, for example, that are very useful to find those cases. And so you can actually extract it into a standalone component, vectorize it using Eve, put it back, and you can see any improvement. And in any case, anyway, if you are confused, if you don't like performances, you think you had a bug, please don't hesitate, ping me or ping the team, and we are going to fix that. So as I said, again, big sorry for not being there in person. I wish I could have. Thanks for your attention, and I will be available this afternoon over the Discord and the rest of the week. So don't hesitate to contact me, to contact us, and yeah, just in case, because before I forgot, we also have. Yeah, we don't care about that anymore. Sorry. We also have. Where are you? Yeah, we also have a Discord. So if you want to get there, for example, we are very, we try to be very keen and accepting. So don't hesitate to come over and we can discuss all of that. So have a good, have a good end of the week. If you want to try much other stuff, don't hesitate. Again, if you're also interested into getting in more depth around that, you can opt over coderecons.com if you want to get more information, more trainings about this subject, and we are very welcoming for new users. So have a good week. I will wait your question in the Discord. Don't hesitate to blast me a lot, and I will answer them as asynchronously as I can. Thanks again for having me remotely. And next year, I will do my best to be there in person. See you all.